Good afternoon, Webinar Wednesday. We're excited to have over 100 attendees for today's for 1 credit from the ACI. Let's get started by giving one lucky attendee a Webinar Wednesday t-shirt for answering this trivia question. Tonight is National Ice Cream Month. What is the most popular ice cream flavor? Answer now using the questions feature on your dashboard. While you're answering, I want to remind everyone that if you've missed any of our previous webinars, you can watch them on our website, webinarwednesday.live, and still receive your CD. Also, please join us for our webinar week, which takes place next week, the 26th to the 29th, plus be eligible for a CE credit, plus into a drawing for a grand prize of an all-expense-paid trip to MD Expo Tampa in November. For more information, visit our website, webinarwednesday.live. Also, just a reminder that the first of our HTM mixers takes place next month, on the 20th, at the Omni Interlochen Home, Colorado. Supported by KBET, please join us for 2 days of valuable networking and vendor engagement opportunities in a slightly modified, less crowded and safer environment. Registration is open, and for more information about the Colorado mixer and our other mixers in Wisconsin and California, please visit HTM Mixers. Okay, let's our webinar Wednesday t-shirt is, and it is congratulations, Linda. Of course, the correct answer is vanilla, but by chocolate. I would like to thank our sponsor, Innovatus Imaging. Innovatus Imaging is to help healthcare professionals provide better patient care. The company offers the is taking a holistic approach by coupling reverse engineering and rigorous testing to ensure the highest quality of repair and yield rates. For more information, visit innovatusimaging.com. Our presenter today is Matt Tomory, Vice President of Ultrasound Center of Excellence at Innovatus Imaging. Matt, you may begin whenever you're ready.
Thank you, Linda. You got Innovatus right 2 out of 3, so not bad. So it is a short A. Welcome everybody to Webinar Wednesday. Today we're going to talk about TEE care, and I know this is a topic that has been discussed a lot over the years by Innovatus and other companies, but we've taken a different approach to this type of material. There's a lot of data within this, and so although the topic has been covered repeatedly over the years, this new approach I'm really excited about. I'd like to thank Ted Lucidi with Innovatus Imaging. This is actually something that he spent a tremendous amount of time on. I'd like to take credit for all this material, but I can't. But this is something that I've delivered material like this over the years along with Ted. So let's get started. So why are we here today? So we're just going to brief introduction of the material, objectives, and outcomes. We're going to talk about cost failures and root cause analysis, and how do these things happen, and how to really streamline this to the direct causes, how to prevent it, and the 4 steps to success. And then our job is to obviously help you succeed. If you're successful, you have satisfied clients, and they have satisfied patients. So really our purpose here is to reduce the frequency, severity, and overall cost of supporting TE probes. And that's key. So frequency, yeah, how many events do you have, but also severity. TE probes have a wide range of damage when they come into Innovatus. At Innovatus, we repair literally thousands of TE probes per year, and the damage can range from a broken locking knob to lock the probe into the system, all the way up to catastrophic failure. The insertion tube's been crushed and opened up, and fluid invasion. So we want to reduce not only the frequency, but the severity, which would lead to overall cost reduction of supporting probes. We want to talk about the root cause analysis of some of these failures, and we're going to present a plan proven to get results. And when we say proven, we've done some pilot programs. We've been in this game for, I think, 11 years now at Innovatus, and before that, Bear Healthcare. I've been doing material like this since the mid to late 80s. And so what we did is we've actually gathered data to show exactly how this program works. So we did pilot this program in 2009. This one pilot customer, and this is just a single example, just to show you folks some of the data, but we had one customer who had 10 TE probes, but yet had 28 catastrophic failures in a single year. So almost 3 catastrophic failures per 1 TE probe that they owned. We were able to cut that in half in year 1 and then an additional 31% in year 2, which translates to a 44% cost reduction for a 3-year trend. So obviously today, I mean, hospitals are being squeezed tighter and tighter on their budgets. I talk to clinical engineering managers and directors almost daily. And what I'm hearing more and more out of the clinical engineering departments is I'm hearing the word budget and cost savings. And that is not something I'm used to hearing as much out of the mouths of people who are running clinical engineering departments. So we're all trying to keep an eye on our costs, and with TEE failure, these costs are unnecessary in a lot of cases. There is some wear and tear involved with TE failures, but there's a lot we can all do to mitigate some of this. So typical costs and failures for an average TE probe, I guess we'll call it. Replacement through the OEM is $15,000 to $40,000, and actually that it can go up to, I've seen some of these higher end TE probes go up to $60,000, and so that average is actually higher than the 22 we have on the slide. Replacement through a third party can be anywhere from $5,000 to $35,000 if you're just buying it. You know, you're letting your fingers do the walking. You're calling your third party providers. You're just shopping around online. But repair through third party is anywhere from $500 to $12,000 or so. And the beauty about repair is using the proper materials and processes and procedures and testing, we can restore those probes back to OEM form, fit, and function and provide a warranty that's equal to or perhaps even longer than a brand new one from the manufacturer. So our data shows that facilities typically experience a 50 to 70% annual failure rate on TE probes. So when Ted Lucidi or myself, when we do an analysis at a hospital, and if they tell us they have 20 TE probes, we make an assumption that about half of those probes will fail, will have some type of failure over the course of a year. So if we take that and we extrapolate the numbers from our facility that owns 10, replacement costs can be anywhere between $110,000 and $154,000. And then we look at lost revenue. And beyond lost revenue, we also have to consider patient satisfaction. With a standard probe, if we're doing an abdominal exam or an obstetrical exam, it's not so mission critical usually. But with TE probes, typically the patient's anesthetized. A lot of times we're in the operating room. And so if a probe goes down, we have patient satisfaction, we have physician satisfaction, you may have an anesthesiologist in the room, the patient may have to be rescheduled. So there's just a cascading effect, negative effects from a TE probe going down. And using a third-party replacement model, the cost could be anywhere between $65,000 and $91,000. And again, you recover all those patient sat factors, such as patient care and throughput and revenue for the department. So let's look at the different types of TE probe failures. So first and foremost, we have physical, where we have different types of damage. Some of these are not so bad, and some of these are borderline catastrophic. So we have, and I'm not going to go through this line by line, but we have all these different types of damages that can occur to a TE probe. And then we have mechanical. And then lastly, we have electrical failures. Now, these are the failures that are associated with normal wear. TE probes do fail due to normal wear and tear. It's just not that often. Typically, when we get a probe in, it is due to something that was preventable. So things that are associated with normal wear and tear can be worn or discolored numbers on the insertion tube, warm bending rubber. That bending rubber at the tip that allows the tip to articulate does get worn over time. And then scratched gouged or damaged distal tip. And the distal tip is the very end of the probe where the array is located. Under mechanical, articulation can fail. Either the range of motion or it can be broken. Articulation on TE probes can be adjusted in a lot of cases. Sometimes it does have to be replaced. Again, this is normal wear and tear. And then electrical, intermittent or broken wiring. Over time, wires break. It's the nature of the beast. If you think about the main cable harness on a TEE or even inside the insertion tube, there are miniature coaxial cables within that those two cables. And those coaxial cables, on average, are 43 gauge. And most of us on this call are technical, and so we think about gauges of wiring. I just rewired a good portion of my house, and I used anywhere from 10 gauge for my hot water heater up to 14 gauge for some of my lighting. Well, we're looking at 43 gauge for transducers, so they're about the size of a human hair. And so we can get intermittent or broken wiring or non-functional buttons because those buttons are mechanical. Most TE probes sent in for repair have failed as a result of preventable damage. So let's look at preventable damage. So most TE probes sent in for repair to Innovatus have failed as a result of gross fluid invasion. Gross fluid invasion is the most catastrophic type of failure we'll get with TE probes. It's also the most preventable. So if we look at how this occurs, so first of all, we have missing seals surrounding the lens. So if we look at this particular probe here, you can see that the sealant around the lens is starting to go in these areas. We can replace that sealant. Separated collars or glue beads. So this is where the insertion tube up here meets the bending rubber. So there is a collar along with a glue bead that seals that up, and you can see that the glue bead is starting to create a gap. And that's where we can get that gross fluid invasion. Damaged insertion tube. Obviously, this is a gross damage on the insertion tube. Damaged bending rubber. We have a nice tooth mark here on our bending rubber. And it doesn't take much. Just a tiny pinhole will allow fluid to get inside a probe. And the cracked distal tip. So this is the tip at the very end of the probe that contains the array and possibly a motor control. And then a flooded control housing. We actually get probes in where somebody who may not have been trained properly in SPD or some other area where the probes are being disinfected may actually immerse the control housing of the probe within the disinfectant solution or the enzymatic solution. There are no probes out there where it is okay to immerse the control housing. So let's look at root cause analysis. So for wear, the missing seals surrounding the lens, the separated collars, the glue beads, and then the seals on the distal tip, that is attributed to wear and tear. Trauma, bending rubber, damaged insertion tube, or cracked distal tip. That is all attributed to trauma. So the probe had some type of impact, some type of bite. It was dropped. I've seen probes slammed in doors. I actually had one account where they were transporting the transducer on a system, and they had a semi-rigid, really thin wall piece of PVC attached to the side of the machine with bungee cords, and it was very creative, and they believed they were doing a great job in protecting the probe. The problem was that that PVC would run into doorways and things like that, and it would kink the probe. And once you kink those insertion tubes, that tube is damaged and it does have to be repaired. And then gaps in training, which would be the flooded control housing. If we have a flooded control housing, somebody has not been trained properly to care for these probes. So common to all these modes of failure, each is detectable. So even if it's wear and tear, it can be detected if the probe is examined properly prior to disinfection or in between patients. So which means that these catastrophic failures of fluid invasion are highly preventable. So we go back to root cause analysis. So wear can cause these missing seals, the separate collars and separated seals, and lack of inspection. So an inspection will catch these things. Same with trauma. An inspection will catch damaged bending rubber, insertion tubes, or the cracked distal tips. And then the inadequate training, of course, is the root cause for the flooded control housing. So to successfully mitigate these costly failures, we really need to develop a comprehensive plan of action. Something that Ted, my counterpart Ted Lucidi, he is currently on a beach in Florida. I think it's called Clear Beach. He may or may not be with us, but he and I, we've separated the country, and we actually go around and we perform these services called a process analysis, where we will follow a transducer through its entire usage cycle. And we want to know how it's used, how it's transported, how it's cleaned and disinfected, how it's stored. We follow that, and we make a lot of recommendations. And these process analyses are highly successful. So we look at where bending rubbers will wear and become brittle. It's the nature of the beast. And the seams and the seals will degrade. Now, what will degrade them even faster and what will wear them even faster is either using the improper chemicals. There are very specific chemicals to clean TEEs down to different OEMs and even different models for the different OEMs. If you look at Philips, for example, you go back into their legacy products, back to for those of you who are a little more advanced in age like I am, you probably remember the HP series, the 1000, 2000, all the way up to the 55 and 7500s. We still see some of those TE probes, all the way up to the latest and greatest Philips probe, which is the X8. Well, if you look in the Philips user manual for the cleaners and disinfectants, they'll vary based on the legacy of the probe. We also see people using the proper chemicals improperly. And so the manual may say, yes, you can use isopropyl alcohol, but what it also states is you can only use that on the control housing, and people may use that on the insertion tube and the tip and the bending rubber and so on. Or they may use the proper chemical on the proper location of the probe, but they may use it for an improper period of time, which can degrade the probes even faster. So we, at Innovatus, we do have a comprehensive preventative maintenance program for TEEs. Depending on the frequency of usage for TEEs, it's not really laid out by time. It's more, with an ultrasound system, usually we do a preventative maintenance on those every 6 months or something along those lines, depending on accreditation and the hospital processes. But with TEE probes, we base it more on usage. Is that probe being used once a day, once a week? And then we base it on usage cycles. So we can do a preventative maintenance on a TE probe. To replace a bending rubber is very inexpensive, along with the glue beads and the locking collars. That bending rubber is very inexpensive. Now, if that fails and you get fluid invasion, now you're getting into a very expensive repair. So this is a true preventative maintenance and can prevent a lot of expensive repairs. So trauma accidents will occur. We get questions all the time. Why do you teach people how to do this? Isn't it in your best interest to not prevent TE damage so you get more probes in? And I guess if you're in it for the short haul, yes. But our purpose here at Innovatus is to partner with healthcare providers to provide these types of services. And yeah, we want your probes when they do break, but we're hoping to help you prevent as much breakage as possible. But accidents will occur. It's a nature of the beast. Some of you on this call know me, a lot of you don't. But my wife is actually a registered sonographer, and how we met was she was one of my clients, and she was breaking probes left and right and asking me to blame those breakages on wear and tear when they were actually being dropped and things like that. So I know sonographers very well. I've been happily married to one for 16 years, and she breaks lots of probes. So accidents will occur. But we can install controls to minimize these opportunities. And we'll talk about those controls in a little bit. And then gaps in training. How recently has training occurred, and are those procedures being followed? Who has been trained? Has there been turnover in the department? Are there different shifts? So you may have trained the early shift, but what about the late shift? Is it a teaching hospital? Teaching hospitals go through probes like no tomorrow. And so ongoing training as you get new students in and out is absolutely vital. So not only do you have to do it on a regular basis, you have to make sure you get all shifts and cover any staff turnover. So what we want to do is we want to perform a process gap analysis to help identify the tools and controls currently in place. So basically, what are they doing today? And that tells us where we need to go from there. Most end users, they really believe they're doing a great job. And when Ted and I do these process analyses, we always tell people, you know what, you're doing a great job, whether they are or not. Because what we don't want to do is tell somebody they're doing something wrong. That's not our job. Our job is to be an advisor, to be a consultant, to help them improve, not to tell them how awful they're doing at the time. I've done probably well over 100 process analyses throughout my career, and I've yet to find an institution where they've done everything correctly or everything to perfection to completely mitigate accidental probe damage. There's always been a gap somewhere where there's an area for improvement. A lot of people believe that their tenure or their experience provides them with a level of credibility. I don't necessarily agree with that. I have an awful golf game because I've been practicing the same awful swing for about 25 years. So just because you're experienced and you've been doing this a long time, have you been doing it correctly for that time? Because TE probes pass through so many hands, there's no single entity. And that's the other problem that we'll get to in just a moment. I'm going to show you folks how many hands these probes pass through in a typical facility. So until we have an objective view of the entire process and we compare those to best practices, these failures will continue. So let's take a look at a continuous quality improvement model. So the first thing we want to do is define our problem. You know, what is our opportunity for improvement, and begin with the end in mind. Obviously, the end game is to reduce damage. And then we want to observe. We want to look at what are they currently doing, gather as much information as possible, and then we compare that to best practices. And then we want to implement changes, and then we go back to define. We want to start measuring again. General Electric, for those of you who are veterans of General Electric or Six Sigma, it's similar to the DMAIC model, the DMAC model, but it's just rooting out a problem and then gathering information, checking up against best practices, and then implementing solutions. So what's the problem here? What are we dealing with? TE probe costs are draining our service budget. Now, sometimes it is a service budget. Usually what we find is clinical engineering typically absorbs a lot, if not all, these costs. And clinical engineering is rarely, if ever, responsible for the care and feeding of these probes. External departments will push back on paying for damage. You know, we can get a TE probe in, you know, a single probe, it can come in 2 boxes and pieces, and the department will say, well, we didn't break it, this is wear and tear. Departments do not want to pay for damage. And the problem with that is within the department, who damaged it? Was it the person who cleaned it? Was the person who used it? Was it the anesthesiologist, the person who transported it? Again, there's lots of hands on these probes. Who broke it? And a lot of them don't even know how much these probes cost. When we do go in and do process analysis and we explain to people exactly how much these probes cost, we get a lot of surprised looks on faces as to the actual costs for replacement and for repair. And we want to begin with the end in mind. So we want to figure out how much are we bleeding on these preventable damaged TE probes, and that'll tell us roughly how much service costs we want to reduce. We want to reduce the number of catastrophic failures. So even if we're still having failures, can we back those level of failures or the severity of failures down? Can we take it down to, I'm going to replace a bending rubber as opposed to I'm going to do a full rebuild on a TE probe. The cost delta there is dramatic. Obviously, we want to reduce the cost to the external departments as well, and that makes for a happier client. So plan for success. We really want to get buy-in from as high up as possible. Because there is so much money involved, depending on the size of the facility, getting buy-in from the C-suite is optimal. If nothing else, getting buy-in from the department heads, the clinical department heads, and clinical engineering is helpful. If you're a clinical engineer and you're just dealing with these broken probes day in and day out, and you're trying to mitigate this, you're probably swimming upstream. So you do need to get buy-in from leadership. So now we're on the observation stage. So gathering information, who, what, where, when, and why. So what are they doing today? And when Ted and I go out and do these process analyses, we follow the probe through every stage of its usage. And we take notes, we take photographs, and we capture the current state as much as we can. So this is a typical process. So let's start with the usage. We'll start over here on insertion. So the probe is used on a patient, and then it's extracted, and then it has to be transported. It goes through gross cleaning, then disinfection, and then it's transported again, then it's stored, transported again, temporary storage, and now we're back to inserting on our patient. So lots of steps here, and every step creates an area where we may have a problem. So here, points at which traumatic damage may occur. So this is where probes may get banged up. That is transport, temporary storage, insertion, and extraction. Are the departments using a bite guard? And again, transport. So when the probe is being physically handled, moved around, that's the area where we see most of our traumatic damage. Now, catastrophic damage. You see, we've moved over now. We're not talking about transport, storage, or even usage, where if somebody doesn't use a bite guard on insertion and extraction, that's a problem. They may nick the insertion tube. They may nick the not the bite guard, but the bending rubber. They may create a breach within that probe. That's a problem. But where the catastrophic damage occurs, where we really kill these probes, is during gross cleaning and disinfection. And that is the process of immersing a transducer with traumatic damage. So during these other stages, we've induced some type of trauma, some type of traumatic damage. But now we take it and we do gross cleaning and disinfection. That's where we take a damaged probe and we make the damage exponentially worse. So now compare. So what tools are available? What are the industry best practices? And how do we compare to best practices? Are we doing everything right? Are we 90% there? Are we 10% there? Most places do a fairly good job. I've seen some real horror shows out there, and I've seen some really clean, tight departments and everywhere in between. But most people do a pretty good job, but there's just areas for improvement. So available tools, OEMs. The OEM makes these things, right? And so their manuals, especially when we look at the chemicals. When we look at TE care, it is critical to reference the OEM manuals for proper cleaning and disinfection of their probes. I would love to get on these types of calls and say, hey, there is one cleaner, one disinfectant that is universal and works on every probe known to man and woman. I can't. It's because the different OEMs, they use different materials, they have different adhesives, different lenses, and so on. So there is no one universal cleaner disinfectant that works on every probe that is approved by the OEM that works on every probe. Storage cabinets, brackets, and tube systems, tip protectors. We'll talk about tip protectors in a little bit. Hypercritical there. Transport bins and probe carriers. Those are hypercritical. Wall-mounted magnifiers. Don't see many people using those, although they would tremendously reduce the amount of TE damage if people were to use them. Leakage meters. TE leakage testing is required if you are accredited by the IAC, the Intersocietal Accreditation Commission. If you're not accredited by the IAC, it is still highly recommended for two reasons. One is for patient safety, of course. That's always our first and foremost concern. But also a leakage test is a wonderful indicator of a probe that has a breach, that has some type of trauma where liquid can get in and can start penetrating the probe, and that's where we get into catastrophic damage. So leakage testing it should be done on every single TE probe for those reasons. Automatic TE reprocessors, those are great because we are handling the probe less. And anytime we handle the probe less, it is better for the probe. Enzymatic sponges, lint-free drying cloths, and visual inspection guides. These are various suppliers for these types of materials. And if anybody wants the websites for some of these materials, they can certainly email me. My email address and Ted's email address will be displayed at the end. And you can email us and we can provide you sources for some of these materials. Innovatus Imaging doesn't supply a lot of this, nor do we have any stake in any of these companies. They're just, they're suppliers known to us to provide quality equipment and materials. And then consultants. As I mentioned, Ted and myself, we do these process analysis. Between the two of us, we've probably been doing this for 50 years. So we'd be more than happy to act as a consultant for any of these folks. So industry best practices, frequent and quick visual inspections by multiple teams. We always want to be looking at this probe because it is passing through so many different hands. Transport bins. Transport bins are critical. I'm seeing less and less pillowcases or red bags, the red bags, blue bags, green bags. Not many people use the bags anymore, thankfully. Some years ago, I used to see probes being transported constantly in pillowcases, which pained me to no end. If we are using a transport bin, we want one probe per bin. Probe coiling, not coiled in a diameter less than 12 inches. If we coil it any tighter than that, that's okay for the main cable harness, but not okay for the insertion tube. If you coil it tighter, the insertion tube may develop a memory, or even worse, if we're coiling it too tight, you may end up kinking it. And if you kink that, there is a metal mesh, kind of looks like a stent if somebody's getting a stent put in, but it kind of looks like that. And once you kink that, you really can't unkink it. You really got to tear it. I've seen organizations where they'll kind of try and re-round that insertion tube. It doesn't work very well. To do it properly, you have to tear apart that probe and replace that metal mesh. So we don't want to coil it any less than 12 inches in diameter. Tip protection in place at all times. This is something I constantly see where people are not doing something so simple, but yet so effective, is using a tip protector. A tip protector should be used at all times, unless you're using the probe on a patient or you're cleaning the probe. Other than that, there are no exceptions. Even when you're storing the probe in a cabinet, those probes get moved around. When people remove them from the holder within a cabinet, that tip may bounce around, and as sensitive as the arrays are on TE probes, the smallest impact can damage the array. And so we do want to see a tip protector on the probe at all times. Thorough visual inspections. Leakage testing. You see that I have here prior to disinfection. That is absolutely crucial. If you would do a leakage test after disinfection, after high-level disinfection, and the probe has a breach, some type of trauma, you will have fluid within that probe. And then what happens when you leakage test, you are now energizing that probe with current, which will blow up that probe, for lack of a better term. So we always want to do leakage testing prior to high-level disinfection. If we look at some of the methods of high-level disinfection out there, there's some passive soaks where the probe is in for 10 or 12 minutes, and if we have a pinhole, it may not be so bad. But then we have something, there's a piece of equipment I've seen called the Medivator, which is a really cool name, by the way. But it is like a high-tech dishwasher that uses high-pressure fluid to disinfect scopes and TE probes, and that will force fluid into the smallest breach of a probe. So we want to do the electrical leakage test prior to any type of disinfection. If we fail the leakage test, as I mentioned earlier, the leakage test is great for two things: patient safety and identifying a breach in the probe. If we fail a leakage test, in all likelihood, you have a breach in the probe. You want to remove the probe from service at that point. Wipe it down with a disinfectant wipe that has been approved by the OEM, but get it in a box, get it off to us. We'll get the repair done. As I mentioned earlier, the difference between a low-level repair, a hole in an insertion tube, or a hole in a bending rubber versus fluid invasion, and if you energize the probe, is exponential. And so if you fail a leakage test, pull the probe, wipe it down if you can with an approved disinfectant, but do not soak it, do not energize it any further. Get it in a box and get it back to us, and we'll get you taken care of. A quick functional and visual check prior to returning to storage. So when you bring it back to storage, take another look at it, make sure there's no breaches. And then the probe stored in a protected manner, hung vertically. We want these probes hung vertically and laid out where the insertion tube is flat. So implement. So all these things that we found, we want to implement some of these. We want to educate all personnel. As I mentioned earlier, do we have new personnel? Do we have another shift? Do we have students coming in? There's some personnel, quite frankly, that cannot be educated. I've had, and I'll call it spirited conversations with anesthesiologists. Anesthesiologists are difficult to get to change the way they do things. If you get into any type of debate at all with an anesthesiologist, your odds of winning that debate are zero. And so you do what you can on educating them. Really, the only way to turn some people who cannot be trained is to start sending bills to that department, and that typically gets attention. Change policies, purchase the tools that we talked about, and implement controls. And we want to measure the impact over time. Are we going through less TE probes, and has our spend go down? So we want to look at the number of instances of repair and the severity of those instances. So without this top-down approach that we talked about, going to the C-suite or leadership, success may be limited. So this is great information, awesome, cool, but what do I do with this? Where do I start? And so we've come up with a very simple, and again, I got to give credit to Ted if he's with us, the red, yellow, green. Everybody understands red, yellow, green. And so we've made this very easy to present to the different departments. So we're going to look at all the different phases of the usage cycle of a TE probe and what needs to be fixed immediately, what is kind of an okay process, and then what's ideal. So how are probes stored? Within a bin, drawer, or placed on a shelf. That is red. We want to immediately change that. A bin is fine for transport because it's a short period of time, but we do not want to leave the probe coiled for an extended period of time. Hung vertically in a closed environment, better, but ideal. Hung vertically in a closed, positive pressure environment with a tip protector in place. There are some storage cabinets out there. There's actually one I looked at about 6 months ago, and the customer thought they were doing a great job. They were hanging the probe vertically in this cabinet, but they kept damaging their tips on their probes, and I couldn't figure out why. So I went and visited them, and as I was following the probe around, I saw one hanging in a cabinet, and I examined the cabinet, and they used these toggle bolts to fasten the cabinet to the walls, and the threads from the toggle bolts were sticking into the cabinet right at the tip level, and the tips did not have tip protectors. And so they were banging the tips of these probes up against the bolts that were used to mount this protective cabinet. So it was kind of a good news, bad news thing. Positive pressure is ideal because these probes are stored in these cabinets post-disinfection, typically. We want positive pressure with a HEPA filter on there, so we're not getting contaminants within that cabinet. So transport, how are we transporting probes? Again, this is where a lot of our trauma occurs. So hand-carried probes, not a good idea. Pillowcases and bags, definitely not a good idea. probe is inspected, and the tip is covered, but it's still in a pillowcase or a bag. The problem with a pillowcase and a bag, it's a variety of reasons, but a pillowcase and a bag, it's a soft container, and so you have this hard connector, which has sharp edges. It may have pins, maybe pinless, but it has sharp edges, and it can be banging around that bag or that pillowcase up against that fragile tip or the insertion tube. So ideally, we want the probe inspected, a tip covered, and placed in our transport bin. So temporary storage. So when the probe is brought into the department for temporary storage, rested on the back of the scanner, never a good idea. Placed within the probe holders of the scanner, never a good idea. Those probe holders are not designed for TE probes. They're designed for standard transthoracic probes. The TE probes, because of their length and just the way they're designed, that is a horrible place to store them. Suspended from an IV pole, a little bit better. These probes do come with typically a little ring, so you can do that. Not recommended. Any of the above employed with tip protection, still not recommended, but left within a transport bin until required. And I should have in there with tip protection. I will add that after this webinar, but left in the transport bin is ideal until required for usage. Extraction and transport. So when it's pulled from the patient and we're getting ready to move it again, hand it off, set on the floor. I mean, some of this is 101 common sense, but set on a table or other object, placed in a pillowcase or bag, none of those are a good idea. Tip covered and handed off, tip covered, placed in a bag, not ideal. We want it tip covered and placed in an approved transport bin. So gross cleaning, and this is what after the probe is used, before it goes into high-level disinfection. So where are the control housing and the connector placed? We don't want it on a flat surface such as a tabletop. All these probes have a ring near the control housing. We want that suspended away from the container where the gross disinfection has occurred to keep fluid away from that connector and the control housing. If fluid gets within the control housing or the connector, it will damage that. Especially with today's contemporary probes, there are some sensitive electronics in both those areas. You get fluid in there and you can damage those. Do a brief inspection, and if they're not doing a brief inspection, we'd like to see a wall or desk mounted magnifier. So leakage testing does not occur, not a good idea. We talked about that. It occurs at the end of disinfection, also a very bad idea because you are now energizing a potentially fluid invaded probe. As we all know, we're all technical on this call, or at least most of us are. And we know that liquids and electricity makes a wonderful conduit for liquid, or vice versa. Liquid makes a wonderful conduit for electricity. And once we get liquid throughout that probe, we will start damaging the sensitive electronics in the connector, the control housing, or the tip. So we want to do the leakage testing prior to or at the beginning of disinfection. So if a leakage is identified, what is the process? As I mentioned earlier, get it out of there. We have a failure, the little red light goes on, or if you're using a quantifiable leakage tester and the leakage is above the preset safety level, remove the probe from surface immediately, wipe it down, and ship it off to us, and we'll get it taken care of for substantially less than a catastrophically damaged probes. We want to look at soak times. There's different disinfectants. If you go through the recommended disinfectants for all the different OEMs, you're going to see, I'm going to take a wild guess, 50, maybe 75 different disinfectants out there. And they all have different soak times. Some different disinfectants may be 8 to 10 minutes, some may be 15 minutes. So are they using the proper soak times for the approved chemical? So with the probe immersed, is the fluid level above the boot or the tube strain relief? We do not want the fluid above the boot or the tube strain relief. Ideally, with the probe immersed, we don't want the level above the 1 meter mark. And I'm a big fan of automated disinfection systems because a lot of them have built-in leakage testers. And so you insert the probe into the automated system, it does the leakage testing. It will cycle the disinfectant through the probe for the recommended period of time, and then it will do a clean water rinse. And by the time you pull out the probe, you're done. So huge fan of those. Dramatically reduce margins for error and touch times. So again, we're going back to storage. We've disinfected the probe and we're transporting it back to our storage area. So you're starting to see a pattern here. I'm assuming that, tip protection, if it's not employed and we're transporting it by hand, not a good idea. If we return to a storage without inspection, not a good idea. Ideally, we want tip protection employed and we want it transported in a bin, a protective bin. And then we also want to do a brief inspection and functional check or articulation check before we put it into storage. So capture the data, and I can provide the sheet for you folks. Again, my email address will be at the end. You can also reach out to us. We have a contact page on the Innovatus Imaging website. But if you'd like a copy of this checklist, certainly reach out to us. I promise we will not spam you, but we'll provide this for you. It's a great check sheet to see what a department's currently doing and compare it against the best practices. Photographic evidence. You look at this particular cabinet here. This particular cabinet looks great. So we've taken the strain off the main cable. We have the connector supported. There's no sharp bends. We're hanging the probe vertically, and you see this nice, lovely, bright green tip protector. So this is the proper way to store a TE probe. If you look at as we talk about photographic evidence, if you look at this bin, this probe is coiled up far too tightly. It looks like it was just kind of chucked into the bin. And then what I don't see on this bin are markings. Is this a clean bin? Is this a contaminated bin? Most of the facilities that I see using bins, they color code their bins. Either the bin itself is color coded or there's a lid for the bin that is either red or green, depending on whether the bin is clean or contaminated, potentially contaminated. So this particular probe is attached to a machine. Very, very bad idea for a variety of reasons. The insertion tube is kind of coiled up, and you can see where on the bottom, with my cool little laser pointer here on the bottom, you can see the insertion tube is somewhere in here. But the probe can get knocked off. The connector is kind of hung. There is a dramatic risk of physical damage doing this. Same with this. We have our tip very tightly coiled across the keyboard, and this could be damaging the keyboard. There are toggle switches. This particular system is a GE Vivid 7. There are toggle switches. As they move this probe around, you can actually damage the console of the machine as well. So we don't want to do that for a variety of reasons. So this is kind of a check sheet that Ted and I use for reporting. So we basically go through this questionnaire. Are tip covers in use? Yes, no, and sometimes. Some places will use tip covers occasionally, but not all the places that they're supposed to use them. And then we go through, have we calibrated the probe before the exam? Have we done the visual inspections, the leakage testing? Are they disinfected for the minimum time recommended, and so on? How are they stored? And it's a yes or no. And again, when we do these, the first few times I did these process analyses way back early in my career, people would look at me because I'd have a clipboard and I'm taking pictures, and I'd get all these looks like, who is this guy? Are we being audited? Is this some type of inspection? And then what I started to do is I'd go in, I'd have the clinical engineering department, a representative from clinical engineering, introduce me to the various department heads as to who I am, what I'm doing, that I'm there to help. They are not being judged. They are not being audited. All I'm there is in a very, very consultative role. And then we have specific recommendations. And these are all recommendations that we can provide you as well. And this is just an example. So this particular one that I'm not sure if I did this or Ted did this, but we made all these recommendations. They weren't using a timer. They weren't using the proper chemicals. Down here, they were using super Santa cloth, and we recommended changing to a OEM-approved chemical. So that's something else that we do during the process analysis. We look at all the different chemicals, and we report back, and we say, okay, these chemicals are approved, these chemicals are not approved, these chemicals are approved for these specific areas of the probe. So we make sure that if somebody is using an unapproved chemical, we work with the department to get that out of there. So reporting and wrapped up. So we list our main findings. We provide recommendations. And again, we include photos. We want to include photos to support our findings and recommendations. And this is a visual chart that we have that is available to anybody who requests it. We don't charge for this. So if anybody wants this chart to hang up in cardiology, SPD, anywhere else where a probe is being handled, disinfected, stored, you are more than welcome to request these posters. We're happy to provide them to you. And then tip protection. We do have these tip protectors available. They're also available from some of those other vendors that we had on one of those prior slides. Again, tip protectors, these things are huge. They're extraordinarily inexpensive. Most of them can be disinfected, so you can reuse them. And then leakage testing. There are multiple different leakage tests out there. Some come from third parties, some come from the OEMs, some will quantify, like this particular one from BC Biomedical. It will quantify the leakage. Some are more passive. This one particular one from Fluke, it just gives you a pass-fail, you know, red button or red light, green light. And I kind of like the red light, green lights. You know, they're preset to certain parameters, certain leakage settings. And if that threshold is breached, the little light turns red. And so you're not trying to explain different levels to people who may not be technical in SPD or cardiology. So quick overview, we're at 50, we got 6 minutes left. So nailed the pace today. So quick review. So we presented the root cause of common failures. We have a proven plan to get the results, and we can help provide you the tools to help you succeed and your departments. The money saved by eliminating these catastrophic failures, a catastrophic failure, we can fix the vast majority of TE probes. Our yield rates on TE probes are the best in the industry, but there's some things that just can't be saved. Some probes are just destroyed. And, you know, can we fix it? Yes. Is it cost effective to fix some of these? Maybe not sometimes. Maybe you're just better off buying a refurb from us or a new one from us. And so the money saved by implementing these processes will more than pay for itself very, very quickly. So for more information, here's our website and the contact information for both Ted and myself. And I want to thank you all for joining us today. Hope you're all safe out there. I'm delivering this from the lovely hotspot of Chandler, Arizona. So hope you're all safe, and I'm looking forward for all of us to get back to some type of normal life in the near future. And I'm hoping to see some of you at the HTM Mixers from MD Publishing. I think there's one in Milwaukee, Denver, and California, as well as the Expo in Florida this November. So now, Linda, if you want to open up for questions.
Yeah, great. Thank you, Matt. Yes, we've had a few questions. The first one is, should clinical engineering be responsible for performing leakage tests?
No. The clinical engineering is not available to do that. That is the responsibility of the department and where the probe is being disinfected. They just can't be there all the time. And the responsibility does have to be a sole responsibility. If you spread that responsibility out, if many people are responsible for something, nobody's responsible. So no, that responsibility does lie with where the probe is being cleaned and disinfected.
Is there some type of PM that can be done on a T probe?
There is. As I mentioned earlier, we do have a preventative maintenance program where we'll get a probe in, and typically we replace the bending rubber, the locking collar, and glue beads, as well as we'll do some articulation adjustments and do a thorough inspection of the probe. When it comes in, we do a high-level disinfection, and then we'll return it that way. But yes, the PMs can be very, very successful at mitigating catastrophic damage.
Great. So can Innovatus help me find the tools that you talked about?
Yes, we have that one page where we talk about some of the tools that are available. And Innovatus, we do act as a consultant, and we don't charge for that. And so if you folks want to reach out to either Ted or myself, we can kind of walk through your processes. I'd love to do a visit. I'm dying to get out of the house. I'm here quarantined in my home in Arizona, and I've been out a few times, but with this blankety blank pandemic, I have not been able to get out of the house as much as I'd like. We'd love to do these things on site, but until things get back to a little bit more semblance of normality, we can certainly do a phone consultation, look at what you got, and see how we can help you.
Great, that sounds like we've actually got time for one more question. Is there a formula to figure out if a department has as many probes as they really need?
It depends on how quickly they go through them. Some places are extraordinarily conscientious, and we see very low turnover. But if you start damaging probes, when you damage a probe, even if we can ship an overnight loaner to you, or we have this really cool program called Rapid Repair where we can turn and burn a TE probe in a couple of days, you're still pulling a probe out of service. And even if we're shipping you a loaner, that loaner goes overnight. So now you're down a probe for 24 hours. So a lot of it depends on how quickly you go through them and on the frequency of your exams. If you're doing an exam every hour, what is the disinfection cycle time? We have to look at how long does it take to process a probe. Can you continue processing the same one if you're only doing 2 or 3 exams a day? Or if you're doing exams all day, you're going to need multiple probes because you're going to be using one while you're processing the other.
Okay, that's great. Well, we're coming up to our hour, so thanks, Matt. That was a great and really informative webinar. And as Matt said, his contact details are on the last slide, so please feel free to email him or Ted. So thank you again to today's sponsor, Innovatus Imaging. And just a reminder that the post-webinar survey and certificate process is automated. So the survey link will be included in the follow-up email, which you'll receive in about an hour's time. Once you've completed the download your. If you have any questions, please contact us at webinarpublishing.com. And for more information about all our upcoming webinars and next week's webinar week, please visit our website, again, Webinar Wednesday. Thanks once again to all of you for joining us. Stay safe, and we hope to see you next time.
Thank you, Linda.